All right, today we're going to venture deep, deep underground. I want you to imagine you have to drill a hole, maybe miles deep, and hit a target that's incredibly small from that distance. It doesn't matter if you're looking for gold or building a skyscraper. You are essentially drilling completely blind. And, well, that's a massive engineering challenge.
So seriously, think about it for a second. Miles below the surface, there's no light, there's no GPS, nothing. You are literally steering a piece of equipment through solid rock in total darkness. So how on earth is it done? Let's dive into this incredible puzzle.
Because out here, in these kinds of rugged environments, getting it wrong is just not an option. A tiny error, even just a fraction of a degree, could mean missing a valuable resource deposit completely. Or worse, it could compromise the safety of a huge construction project. The stakes are, incredibly high.
So how do we solve this problem? I mean, a standard compass is totally useless down there. There's way too much magnetic interference from all the rock and the equipment itself. The real answer, it turns out, lies in technology that doesn't need to see the sky to know exactly where it's going.
The solution is something called a gyroscopic survey tool. Now, the easiest way to think of it is like an inertial navigation system, kind of like what you'd find in a rocket or a submarine, but it's been shrunk down to fit inside a drill rod. Deep inside, a gyroscope is spinning incredibly fast, and that allows it to maintain its orientation in space. By measuring how the Earth itself rotates around it, the tool can calculate the direction of true north, giving it this unshakable reference point to map its own path.
And here's a fantastic modern example of this tech in action, the IMDX Gyro Sprint-IQ. This thing is a great showcase of the advanced systems that make this kind of high-speed, high-accuracy underground surveying a reality today.
So what does it actually take to run one of these surveys? Let's break down the essential hardware. It's a whole kit, and trust me, every single piece is absolutely critical for success. Okay, so here's the whole shebang. You've got the super sensitive probe, you've got the running gear that protects it on its long journey down, and you have the depth encoder. It all packs into these rugged cases because, remember, these tools have to work perfectly in some of the most brutal environments on the entire planet. Now this is the core component right here, the gyro probe. Inside this tough metal cylinder are these incredibly sensitive gyroscopes and accelerometers. As this tool travels down the drill hole, it's taking thousands, literally thousands of measurements every second, building a picture of its path in real time. It truly is the heart of the system. Of course, knowing your direction is pretty useless if you don't know how far you've gone. And that's where the depth encoder comes in. It sits there and precisely measures the cable as it spools out, tracking the probe's depth with millimeter accuracy. It's basically the mission's odometer. And finally, we have mission control. This Panasonic ToughPad is the super rugged tablet that runs all the specialized software. Operators use this to program the survey, to monitor the data as it's coming in, and then to download the final results. You got it, it's the brains of the entire operation. So, how does this all come together out in the field? Well, like any complex mission, preparation is absolutely everything. Assembling this tool correctly is like a critical pre-launch sequence where every single little detail matters. This diagram really shows you just how complex it is. Every component has to be connected with total precision. If just one connection isn't perfectly tight, the whole thing could come apart miles underground, and that would be a really costly and dangerous failure. So it all boils down to a strict pre-flight checklist. First, you verify the battery is fully charged, no excuses. Second, you securely tighten every single connection. And third, you have to select the correct survey mode for the specific drill hole you're working on. And that third step is actually pretty fascinating. The tool operates differently depending on the angle of the drill hole. So, for example, a downward drill hole might use something called a continuous north-seeking mode. But if you're drilling upwards, the tool has to switch to a totally different mode to make sure it gets the most stable and accurate measurement possible. Okay, so once the hardware is all assembled and ready to go, it's time to program the mission. This is the part where the operator uses that ToughPad to tell the tool exactly where it is on planet Earth and what the survey plan is. The software, you'll see, is designed to be really straightforward because out in the field, there's just no time for confusing menus. The operator creates a new project, they define the drill hole, and then they input the precise starting coordinates of the hole. And these are the key mission parameters. The tool needs to know the project and drill hole names just for data management. But crucially, it needs its exact starting position on the globe. We're talking hemisphere, latitude, and longitude. This gives it that critical "you are here" marker for its underground map.
So after all that prep work, the careful assembly, the checks, the programming, what's the actual payoff? What does this whole complex technological mission really deliver at the end of the day?
The payoff is this. The tool combines all of its direction and depth data to create a highly accurate, three-dimensional digital map of the drill's path. It literally transforms something that is completely invisible, buried deep in the earth, into a precise digital model that you can see and analyze on a screen. And this matters a lot. This technology allows mining companies to find and extract resources with surgical precision, which dramatically reduces waste. It helps engineers build much safer tunnels and foundations. And for scientists, it gives us a much clearer picture of the planet that's right beneath our feet. Ultimately, this whole thing is about more than just drilling. We've developed these incredible tools to map an unseen world right below us. And it kind of makes you wonder, from the deep oceans to distant planets, what other invisible worlds are we just now finally learning how to see?